Hello students, welcome to the third and last part of section 7.1, and this is the part that you get into the application, so hopefully you'll find this real interesting. This is a couple of physics applications that we'll look at since we've been talking about angles. Alright, so to begin with, what we're going to be talking about is angular velocity, and this is a little bit of physics. And you've certainly seen this before. In fact, you can think about angular velocity every time you drive your car. So what angular velocity is, it's a measurement that represents the motion of a circle as it rotates through an angle in radians over a period of time. The formula that we'll use is omega equals theta over t. And what that means is omega is what we use for the angular velocity. It's a Greek letter. Theta is the central angle of the circle that's swept out in radians, and then t is the amount of time. The units, usually what you're going to see on this is radians. You want to write this down, radians per some unit of time. So for example, you might see radians per minute, or you might see radians per second or something like that. Okay, so what I'm going to do on this is I'm going to show you a couple of little videos, little applets that I found on the internet. One way to think of angular velocity is think about next time you get in your car and drive, you'll probably have a tachometer in your car. And what that does is that measures the crankshaft of your engine is actually turning, and that's, making the pistons change and so forth. So what's going to happen on this is measured in rotations per minute. So it's telling you how many times the engine's crank turns in a particular minute. And this is in thousands, so your engine turns really fast. So if the dial is up like that, if it says 3 RPMs, if it's 3 RPMs, that just means every time a minute goes by, it goes through 3,000 revolutions is actually what that means. If it was only going 3 revolutions, your engine wouldn't perform much work. So that's in thousands. That's the idea. Okay, let's see. I'm going to pull up this thing for a minute and show this. I'll show this a couple of times on here, and this is sort of a nice little applet on here. So if you were to think of a bicycle sprocket or a motorcycle sprocket, what the angular velocity is going to be is what is the angle it turns in a unit of time. So it might turn pi radians in a second, or it may do 2 pi radians in a minute, or something like that. So I'm going to start this. And what you're seeing on this is this thing, this big sprocket here, has an angular velocity it's reading out right now on this one of 1.2 radians per second. So every time a second goes by, you can kind of start right here. So there's like 1 second. It's going to go through 1.2 radians in that particular second. Notice this other sprocket, it has a different angular velocity, because it's a smaller sprocket. And you'll notice on this is as that gets smaller, it's kind of hard to see, but it starts rotating faster. Okay, as it gets bigger, as the circle gets bigger, notice that it's rotating slower and slower. So that's what we call an angular velocity. Okay, all right, another thing I wanted to just show kind of real quick on here is, well, there's this turntable I wanted to show you, and then I'll come back to this in just a minute. So you can think of angular velocity, just think of some circle rotating, and it's how many rotations this makes in a unit of time. So you see that little kind of pink dot? It was doing a certain rotation in a unit of time, all right? Okay, so let's see. Let's do an example on this, kind of get started on this. So you have a Ferris wheel, like in a carnival. And what we have on this, it says the edge of the Ferris wheel turns at an angular velocity of 12.5 radians per minute. And we're going to find the angular velocity at a point 10 feet from the center. Okay, so I'm just going to write that down. If you have an angular velocity, you use omega, and we're just going to say that's 12.5 radians per unit per minute. Okay, now what the question's asking is this. Okay, what that's really saying is every time a minute goes by, it sweeps through 12.5 radians. And I want to just kind of mention to you that if this is radians, and if I wanted to take this to degrees just for the context of this, then remember what you do is you multiply by 180 over pi to change that back to degrees. So I'm going to do that on my calculator, and I'm only doing this sort of for the context of what I want to show you. So I'm going to do that, divide by pi, and this is going to be more than one revolution around the circle. See, that's about 716 degrees. So every time a minute goes by, this thing is going through almost 2 rotations, all right? So here's the question. And it turns out on this one, you don't have to do any calculation whatsoever. It says, what is the angular velocity at a point 10 feet from the center? So I gave you that the angular velocity at the edge of the circle, that would be where you're writing on this, that's 12.5. I'm just saying, well, what if we went out like here? And let's say that that is 10 feet from the center of this Ferris wheel. Okay, the question is what is its angular velocity? Well, it's going to be turning at the same rate. So it's going to have the same answer. So that angular velocity at 10 feet is also going to be 12.5 radians per minute. Okay, that's just kind of a concept I want you to catch on to. All right, so I'm going to show this in 2 different ways. I'm going to take a look at this little video. I guess some teacher, or physics teacher or math teacher must have made this up. And you may not be able to see this very good. Yeah, things not coming up very good. Okay, well, you can kind of see that on there. There's two little models, I guess, going around there, and they're rotating at the same rate. One of them, the guy that's the red one, is actually closer to the center of the circle than the blue one is, but they're still rotating. They're still making the same number of laps in a unit of time. So they're sweeping through the same angle in a unit of time. Okay? So hopefully that kind of helps you with that a little bit. I'm also going to look at this applet that I have. You might be able to see that a little bit better now. So that's showing that they have the same angular velocity. All right? So next thing I'm going to do is I'm going to go back to this applet one more time, and I think this will make this pretty clear to you. That's not what I meant to do. I'm looking for the pulleys. Okay. So let me load this up real quick and just show you this real quick, and then this should clarify it if that didn't, hopefully. So the idea is right now these 2 sprockets have different angular velocities. Which one's turning at a faster rate, rotating? Which one's rotating faster? Yeah, this one's rotating faster. But notice if I went through and I made it exactly the same size, okay, if I made them both have a radius of 5, well, it's hard to stop that exactly. Well, you can see now, aren't they rotating at the same rate? Okay, I mean, if the radius is exactly the same, then they're going to rotate at exactly the same speed. Okay, so hopefully that clarifies that. Okay, so let's go to the next page, and what I want to look at on this then is a couple of applications with this now. So we have example 2 says a tachometer of a car is reading 2.8 RPM, which stands for revolutions per minute. We're going to find the angular velocity in radians per second. Okay, well, first of all, if you're given a measurement in RPM, it is an angular velocity. So we're going to say omega is 2.8 revolutions per minute. So I've already given you an angular velocity. So it's real important when you're doing these word problems to know what you're given. And I know that's an angular velocity because it's in revolutions per minute. If I give you something in radians per second, it's also an angular velocity. So really all we're going to do is do a conversion on this then. All right. And these type of conversions could be new for some of you. If you've taken science like chemistry or physics before, you probably learned how to do what we call dimensional analysis. If not, you may have never heard of that before. So here's what we're going to do. We want our answer to be in radians per second. We don't want it to be in revolutions per minute. So I want the revolutions to cancel out and be converted to radians. Okay? Well, there's a connection there. Okay? And I want you to think about this. What did we learn? Every time you go one revolution around a circle, how many radians is that? Remember, pi radians is 180. What's one full rotation? Right, that's 2 pi radians. Okay, so by doing that, the units cancel out. Now I'm in radians per minute. Okay, now I'm going to do one other conversion. Okay, I don't want minutes, I want seconds. So if the minute is on the bottom, you need to put it on the top of the fraction so they'll cancel, and we want to end up with seconds. Now you got to know the connection between minutes and seconds. So what is 1 minute equal to? Yeah, that's 60 seconds. Good. Okay, so these things are called unit fractions. And what I mean by that is you have a conversion factor. So 1 revolution is the same as 2 pi radians. And 1 minute is the same as 60 seconds. So they represent the same thing. So they're really a unit fraction. Okay, now here's what happens. The units cross out. Notice that we are left with an answer in radians per second. Now all we got to do is just calculate this. So I'm going to do this in a couple of steps on the calculator. You don't have to, though. I'm just going to go straight across the fractions. So 2.8 times 2 pi. And I'll record what that is. You don't have to necessarily. So that's 17.59291886. And then I've got straight across on the bottom, I get 60. Okay, so I'm going to take that, divide that by 60, and then that'll give us the answer. So that would be about 0.29 radians per second. So every time every time a second goes by, you go through 0.29 radians. Now to get some perspective on this, the way you convert radians to degrees is you multiply by 180 over pi. So I'm only doing this to give you a little bit of a perspective. What this really means is every time a second goes by, you went through 16.8 degrees in your circle. Okay, so this is the answer. I want that in radians per second. You don't have to convert it to degrees, but I want to kind of do that to give you a little bit of a context. Okay, so the only way to learn this stuff is just to try and do it. Always write down what you're given and try to figure out where you're going with this. So I'm going to let you go ahead and pause the recording for a few minutes, and you can see what you get on this. Okay, come back and check it when you're ready. Okay, so I'm going to go ahead. I went ahead and posted the answer to the first one. I'm going to carry you through number 2 and kind of finish that up and explain it as I go. So really the thing that you want to understand on this is always understand what you've been given. So since it's in revolutions per minute, that means it's an angular velocity. So I'm just writing down what I was given. I was given 1.5 revolutions per minute. And then I'm doing a conversion problem. I'm changing it to radians per second. So again, think of it this way. I want revolutions to go away, so I put the revolutions on bottom, and I want the radians to be on top. The connection is every time one revolution goes by, you have 2 pi radians. Then I want minutes to go away. Minutes on bottom has to cancel with minutes on top, and I want to end up with seconds on the bottom. The conversion factor is every time you have 1 minute, you have 60 seconds. And then from here, you can see what I did on the calculator. I multiplied straight across. 1.45 times 2 pi gives the 9.11. Then I divide by 60. So you should have gotten 0.15 radians per second. And just for a little perspective, if I convert to degrees, I multiply by 180 divided by pi. That would mean every time a second goes by, you sweep through an angle of 8.7 degrees. And that's pretty easy to imagine in your mind. Okay, so next thing I want to show you is what I'm doing here. Again, I gave you omega. I gave you the angular velocity because I gave you the right units for angular velocity. You can either be given radians per unit of time or RPM typically. So we want to just convert this to RPM. So it goes like this. We don't want radians. What we want to end up with is revolutions per minute. So the idea is if I want radians to cancel, I need to have my radian in the bottom so it will, and I want to connect that to revolutions. So what we know is 1 revolution is the same as 2 pi radians. Okay, so that will cancel that out, and see now I'm in revolutions per second. Well, I want to convert the seconds to minutes. So if the second starts in the bottom, it's got to cancel with the seconds in the numerator. And then I want to end up with minutes in the denominator. So the connection is 1 minute goes with 60 seconds. You don't want to get that backwards. Okay, so the seconds will cross out. And then basically now you're ready to go to the calculator to get the answer on this. Okay, now this is something you got to be really careful about. If I go 2.9 times 60, you want to get that answer, just kind of a rule of thumb. That's going to be 174, and then divide by 2 pi. Now, let me do something that I see students do a lot. If I go 174 divided by 2 pi, that is not the correct way to put that in the calculator. That's totally wrong. You need to make a note of that. If you do it this way, the calculator is following order of operations. It's doing division and multiplication left to right, which is what order of operations says to do. So it's doing 174 divided by 2, getting the answer, then multiplying by pi. That is not what you want the calculator to do. You want the calculator to figure out what 2 pi is, and then do the division. So notice you're going to get a totally different answer. Okay, that's the right way to put that in your calculator. So that's a really good thing to make a note of. I see students do that a lot in this class. So that would be 27.7, and let's see, we're in revolutions per minute, and you can just write RPM if you want to. So we end up with 27.7 RPM. Okay, so that's what you should have got. Those two problems really were an exercise in unit conversion to begin with. Okay, so that'll take us through that part. Okay, so the next thing I want to kind of look at down at the bottom of the page, we're going to go ahead and look at linear velocity next. And linear velocity is a different idea. Okay, it's not the same as angular velocity. So just kind of talking through this, linear velocity of a point on a circle is a measurement of the distance the point moves in a unit of time. So you have some circle rotating. It's a distance over a time. The formula you'll see me using is it's v equals s over t. V is the linear velocity. S is the arc length. And remember, we learned a formula, s equals r theta. That's the length of an arc, is found by multiplying the radian measure of the angle times the radius. And then t is the time it takes the point to move through a specific arc in the circle. The units are a distance over a time. So an example of this would be like miles per hour. That's what you're used to when you drive your car. Meters per second. Okay, that's just a distance over a time. Okay, and I'm going to pull up this applet again, and I'm going to show you what the difference between the angular and linear velocity is in this diagram. Okay, now I'm going to start this. Now, what the linear velocity is it's the distance this red dot travels in a unit of time. Okay, so right now you would just measure how far it's going every second or how far it's going every minute. So it's actually traveling a distance. That linear velocity has nothing to do with the rotation of that, although it is determined by the rotational velocity. It's just simply a distance it's going over a unit of time. Now, if you look at this right now, these linear velocities are being calculated right now, and we're going to learn how to do that. So what's happening is they're the same. It's calculating right now that they're 6 meters per second. And if I change this, I want you to notice on this, if I change this, look at that, it's still staying the same, okay? It's not changing ever. Regardless of how big or small these circles are, the linear velocities of these two wheels are the same because that thing is traveling a certain distance in a unit of time. And it doesn't matter how small or how big one of the wheels are. See, they're still the same. The angular velocities are different, and the only time the angular velocities are equal is if the size of the circles are equal, like they are right now. So if you look at this right now, the angular velocities are the same. They're rotating the same, but also this red dot is just continuing to travel the same velocity constantly. Okay, so that maybe will help you understand that a little bit better. Okay, so that's the idea. Let's go to the next page. And on this next page, the car's speedometer is what measures linear velocity. So in miles per hour, what that's really doing is it's your speedometer in your car, it's really measuring the distance a point on the car's tire moves in a unit of time. So you can think of that applet I showed you a minute ago, that red dot would be like a point on the tire, and it's how far it goes in a unit of time. So that's what the speedometer is doing. Also, kilometers per hour for the metric system would be a linear velocity also. Okay, so the next thing is you want to get clear on the relationship between these two velocities. Most of the problems that you do in your assignment are going to be based on this relation between the two. Okay, so what we have is we can get a formula. The formula that relates the two is this. Okay, so that's got v is the linear velocity, omega is the angular velocity. So it turns out that the relationship between the two is the linear velocity is just the product of the angular velocity times the radius. Okay, that's what it is. Now I'm going to show you where that comes from and just do a proof, but you'll need to know this formula and what everything means in it. That just is how they interconnect. So what I'm going to do is I'm going to show you how to do this, and I want you to write this down. So step one, you need to just write down the formula that we learned for linear velocity just a few minutes ago. The linear velocity is the arc length over time. It's the arc it moves in a circle in a unit of time. Okay. However, we learned earlier in this section that S is r theta. So what I'm going to do is I'm just going to replace that S with r theta. So I get r theta over t. Okay. Now, I'm going to split this up so it's r times theta over t. These two things mean the same thing. Now, I want to see if you know this. Do you know what that is? Yes. Okay, theta over t is the angular velocity. So I can just plug it in. Okay, so I have r and then replace theta over t with omega. So what I get, the conclusion I get, is the linear velocity is the same as the product of the radius of the circle times the angular velocity. Okay, so that's what we're going to use quite a bit in these next examples. Okay, so we've learned really three key formulas in here so far. Okay, so let's read this, this example, and let's go through this and kind of see where we are at with this. Okay, so this says you have a truck with a 28-inch diameter wheels that are traveling 55 miles per hour. So we're going to find the angular velocity of the wheels in radians per second. Then we're going to find how many revolutions are made in a minute. Okay, so to begin with, I'm just going to draw a circle to represent the tire and just kind of get that going. So what this says is, remember the diameter of a circle is the distance all the way across the circle, so that's important. So you have the diameter, and I'm just going to write down here kind of what we're given in the problem. So we're given that the diameter is 28 inches. Now, how do you find the radius of a circle if the diameter is 28? Yeah, right. Okay, so the radius is going to be 14 inches. Okay, so that's what's important. That's an important part of this problem, is we have the radius is 14 inches. Okay, so we've got, that's what that gives you. Now, the next thing, and this to me is the whole key to the problem, is you need to know what that 55 miles represents, 55 miles per hour. Okay, well, the person's obeying the speed limit, so that's cool, but what does it represent? Is it a linear or is it angular? Okay, that's what would show up on your speedometer. So that means the linear velocity, V, is 55 miles per hour. Okay, you should always, when you do these problems, write down what you're given. Okay, that's a real key when you're doing this or physics or word problems in general. Write down what you're given. You have to read the problem and understand what you're given. Now, the next thing is we're going to figure out, well, what are we trying to find? Okay, we're going to find the angular velocity. Okay, so that means we want to find the angular velocity, and what letter represents that? Omega does. Okay, so here's what we have then. We learned these formulas. You basically learned the formula: linear velocity is s over t, angular velocity is theta over t, and then we learned just a few minutes ago v is equal to r omega. Now, which of those formulas is going to be helpful for us? See, I gave you r and v. So notice, hey, I already gave you r and v, then it's easy to find omega, isn't it? Okay, so that will tell you which formula to use based on what you're given. All right, so let's write that down. We just have v is equal to r times omega. We want to solve this equation for omega, so I'm going to do this. I'm going to divide both sides by r. So to isolate that, I get omega, the angular velocity, is v over r. Okay, so now I'm pretty much ready to put this together. Okay, all right, so now we just plug in. So the linear velocity is 55 miles per hour. And then the radius is 14 inches. Okay, so this is going to be what we have to do to find that angular velocity then. All right, so now what I'm going to do is we got some unit problems here. So at the side of the paper here, well, I'm going to just kind of come down in this little area right here, and I'm going to do a quick conversion. Okay, so what I'm going to do is we can either change miles to inches or inches to miles. It doesn't make any difference. Okay, I'm just going to change the miles to inches. I'll get a real big number, but you can go backwards too. So you have to know some unit conversion factors. Okay, so the first thing is in 1 mile, you live in, if I'm recording this in Denver right now, so 5,280 feet are in a mile. So if by doing that, now I'm in feet. Okay, well, I want to change to inches. So we know that 1 inch, or no, I'm doing that backwards, sorry. We know that we want to get rid of feet. We want to end up with inches. So we know there's 12 inches in 1 foot. Okay, so we got to do this unit conversion before we even finish this problem. Okay, so now what we have is we have this. We'll go ahead and take the calculator. And I'll go ahead and calculate that now. So I'm going to take the 55 miles times the 5,280 feet that are in a mile times the 12 inches that are in a foot. And I'll give a big number, and that's okay. So that's giving 3484800. So that is, did I miss something? Yeah, I missed something there. Let me write that out better. Okay, so that is 3,484,800 inches. That's a lot of inches in 55 miles, okay? So here's what we do now. What we'll do is we're just going to have the 55 miles is 3,484,800 inches per hour, all over 14 inches. Now what's going to happen is these things are going to cancel out. So what you end up having is the inches cross out, and we end up with something per hour. So what I'm going to do is take this number, divide it by 14, and now we're going to be in radians per hour. Okay, so we would write that as omega equals, and let's see, that's 248,914.3, and that's radians per hour. Okay, now remember, radians is unitless, so I put it in there as a placeholder. Technically, it turned out to just be per hour, but we want to use radians per hour on that. Okay, now we want this to be in radians per second. So we need to do one more unit conversion here. So what I'm going to end up doing now is I've got 248,914.3 radians per hour. And then I need to multiply that to get radians per second. Okay, well, what I want on this is I want to change hours to seconds. Well, there's two ways to do this. You know that in 1 hour, there's 60 minutes. That puts you miles. I need to put minutes. Okay. All right, and let's see. So now we're in radians per minute. And if you want to do the next step on this, we would say in 1 minute, there are 60 seconds. Or you could just do 3,600. There's actually 3,600 seconds in a minute. Okay, now I'll just take the calculator and I'll do this then. So you got to be careful about how you do this now. So it's 248,914.3. Now, if you did this, I see students do this all the time. That is wrong. The correct way to do this is 248,914.3 divided by, and then you can have 60 times 60 in parentheses. Okay, because whoops, not like that. Do the parentheses. Okay, you do that, and you'll have a correct calculation. Okay, so that's going to end up giving me now 69.1 radians per second. And that is the final answer to the problem. That's what we're looking at. All right. Okay. So every time a second goes by, you sweep through that many radians. Again, for perspective, if you multiply this by 180 over pi, this will give you the angle in degrees. So you go through 3,961 degrees on a circle every time a second goes by. If I divide this by 360 to get more perspective, that means every time a second goes by, you go through around 11 rotations in a circle. So that's pretty darn fast, isn't it? Okay, so if you're going 55 miles per hour on this truck, that wheel is turning really fast. Every time a second goes, it's 11 rotations. Okay, all right. So that's it. Now the next question is how many revolutions are made in a minute. That's kind of what I just answered there, I guess. So I'm going to do this like this. To finish this up, I'll just do this over here. So we have 69.1 radians per second. We're going to change this to revolutions per minute. Okay, so I go like this. Like we've been doing, every time you have 1 revolution, that's 2 pi radians. Okay, and then in seconds, we want to change seconds to minutes. So there are 60 seconds in 1 minute. Okay, so notice now if we do those things, we're in revolutions per minute. Okay, now I can go to the calculator and we're done with it. And again, watch how I do this on the calculator. You want to go 69.1 divided by parentheses. Oh, hold on, Brad. You got to multiply, so we go multiply by 60 seconds. Let me do this right. Okay, a rule of thumb to always follow, if you do this, you aren't going to go wrong, is put the numerator of a fraction in parentheses and put the denominator of the fraction in parentheses. That's just kind of a important rule of thumb. Okay, and if I do that, then the answer to this problem would be 659.9 revolutions per minute. So every time in 1 minute, you're turning through just about 660 revolutions. Okay, that's pretty fast. All right, so that's the idea. Okay, so see, this is kind of what you're getting into. There's a lot of work on these problems, but most of it's actually unit conversions, so you ought to be solid with that. All right, any questions or problems? Okay, this is usually the challenging part of the section, the most challenging part for students. Okay, so I'm going to go on and do this example and a couple of more, and then we'll kind of finish up with letting you work out a few problems, and I'm going to maybe do one last big example to show you something. All right, so again, let's read this problem, and it's always good to kind of write down what you're given in these problems. Okay, so this says find the distance along the arc on the surface of the Earth that subtends a central angle of 10 minutes. 10 minutes is a fractional part of a degree, so it's a 60th of a degree. And then the radius of the Earth is approximately 3,960 miles. Okay, so just for a little visual perspective on this, I'm going to draw a circle to represent the Earth. Okay, so there's planet Earth, and what we're going to have is the radius, and I think this is relatively accurate, is that radius is 3,960 miles. So that's your radius. Okay, the other thing is you're given the angle theta, and that angle theta that it's going to rotate through is 1/60th of a degree. Okay, now I'm not going to draw this to scale. I'm just going to say, okay, that's my angle theta. 1/60th of the degree is not drawn to scale. So what we're going to do is we're going to find the distance along the arc of the surface of the Earth that subtends this central angle like this. So we're going to go like this. So you're actually going to find that angle, that arc like this. Okay. Now this problem asks nothing about velocity or anything. It's just asking about that. So what we would do on this then is, well, what formula do you use? I've given you r and theta. So what do you use? You use S equals r times theta. And again, theta has to be in radians when you put this together. Okay. All right. I could have shown this in an earlier part of the section if I wanted to. All right. So let's do that. Theta is 1/60th of a degree. Remember, the correct way to change degrees to radians is to multiply by pi over 180. Now what I'm going to do on this is use my calculator, and I'm just going to use decimals on this, I think. So I'll go straight across. I'll get pi divided by, and again, you want to do parentheses here, so that's 60 times 180. I'm going to use whatever decimals come out on my calculator and do the rounding at the very end. Now this is in scientific notation. Okay, so I'm just going to write that down as 2.9, I'll round it, 2.91 times 10 to the negative 4. And that's in radians now. Okay, so all I have to do now is just take the radius, which is 3,960 miles, and then multiply by the radian measure, and then I'll have my answer. Now, if you don't know scientific notation, let me show you how to do that. Usually on the TI calculators, you have this EE key, which puts that in scientific notation. So what I'm going to do on this is just go 3960, and then in the new parenthesis, I'm going to go 2.91, and then EE, and then negative 4. So that's a real small number. And then do that calculation, and then that will give me the solution to that problem. So that is about 1.15 miles is approximately what the length of that arc is. That's a real tiny angle, so that's a real small distance. That's the reasoning behind that then, okay? Okay, so that's what that would mean then. Now, if I wanted to find a velocity, like or something on that, there's a way that you could find like a linear and angular velocity based on what you know about the rotational speed of the Earth. And we do know it's about 24 hours for one rotation of the Earth approximately. So that's the idea. Okay, so what do you think? Yeah, mostly what you have to do, and I can't stress this enough, is you have to know what you're given. And then you got to know what you're finding. And when you're trying to find something, you got to know what formula to use. So I always recommend, after you read the word problem, write down what you're given and write down the correct variables. Write down what you're finding and write down the correct formula. That's really what it boils down to. Okay, so going on to this next one. This says you have a wheel of radius 15 inches is rotating at 20 degrees per second. And we're going to find the angular velocity in RPM. So again, let's write down what we're given. And let's use the right variables. Well, this is pretty obvious. Okay, the radius is 15 inches, and we use R for the radius. But what is this? 20 degrees per second. It's a rate, so it's either got to be, it's either V, angular, or linear velocity, or it's angular. Which is it? Yes, it's angular velocity because it's a rotation it's an angle per unit of time, although it's in degrees per unit of time. So that is 20 degrees per second. Okay, so that's what that is. Now, what are we trying to find? We're trying to find the angular velocity, which is omega. Well, look at that. We already found it. I already gave it to you. What's different in this problem is we just got to change the units, okay? So let's kind of start like this then. So we know that we were given omega is 20 degrees per second. Okay, well, one thing that we need to do on this is we need to do a conversion. So we're going to convert this to radians. Okay, we have to be in radians, so we're going to multiply that by pi over 180. Okay, and I'm just going to get a decimal on this. It's fine to do that. Use a lot of decimals. Use at least 4 or 5 decimals when you do that. So I'm going to go 20 pi and then divide by 180. Don't need parentheses on the denominator because it's just one number. Okay, so that's going to give about 0.3490658,504. I recommend just writing all the decimals down and rounding at the very end. Okay, so I'm going to write this like this. We have omega is 0.3490658,504 radians per second. Now we got to change this to RPMs. Okay. Okay, so what I'm going to do is I'm going to do my unit conversion now. Okay, so I'm going to do this. I want this to be in revolutions per minute. So get the radians to cross out. Okay, what you do is you know there's a conversion factor between 1 revolutions is 2 pi radians. Okay, so we got that taken care of. Now get rid of the seconds and change the seconds to minutes. So you have to have seconds on top, minutes on bottom. We know that there are 60 seconds in 1 minute, like that. Okay, now to do this, just watch how I do this on the calculator. And you can do this in one step if you want to. Just do it like this. Just go parentheses 0.3490658504 times 60. You want the calculator to do that numerator. Now we want the calculator to do the denominator, which is 2 times pi. See, that's a multiplication problem. Then you want it to divide. You're controlling the order of operations by doing that. And then that would give you an answer which is about 3.3 revolutions per minute. Okay, so that's how many revolutions that wheel goes around in 1 minute, which is pretty slow. And that makes a lot of sense. 20 degrees in a second, that's not too fast. That's a pretty slow-moving wheel. Okay, now the next thing is we're going to find the linear velocity. Okay, well, let's see, what do we know now? We know the radius is 15 inches, and now we know the angular velocity is 3.3 RPMs, or if you go back a tad bit here, it was actually 0.3490658,504 radians per second. So we had that. Okay, I have RMM. I think I meant to put RPM there. Okay, so that's kind of what we're given. Now we're going to find the linear velocity. So that means we're finding V. Okay, now we have these formulas again. We have, I want to stress that what you always kind of do is, okay, the key formulas is V is S over T. omega is theta over t, and v is our omega. We need to know which one we're going to use. Well, if I want to find v, and I already know r and w, which I know, then this is the correct one to use. Okay, so let's write down v equals r omega. Now, in this formula, you really need to have that in radians per unit of time, and then this has got to be in miles per hour, so there is going to be a lot of unit conversion on this thing then, okay? So basically what we do is we want to start like this, okay? We want to just take the radius, 15 inches, and we want to multiply that by the angular velocity. Now, I wouldn't do RPM. You want to use the one that's in radians, so let's just use that. Okay, so I'm going to write that down as 0.3490658,504 radians per second. If you rounded that off to 4 decimals, it probably wouldn't make much difference. But you always want to use it probably at least 4 decimals. Okay. All right, now we got a bunch of unit conversions we got to do. See, we want the answer in miles per hour. All right, so that's what we're going to do. We want the inches to go to miles. All right, so what we have is we know that there are 12 inches in a foot. Okay, so now we've changed to foot. And we also know there are 5,280 feet in 1 mile. So we have that. Okay, just get the units to cancel and end up with what you have. So right now we're good. We're in miles. Okay, we want miles per hour. Right now we got miles. Right now we got miles per second. So we got to change seconds to hours. So one thing you can do this in one step if you want to. There are 3,600 seconds in 1 hour. Okay, you can do that if you want to, or you can do that in multiple steps. And what happens, that crosses out. So now we are left with miles per hour. Okay, 60 seconds in a minute, 60 minutes an hour, 60 times 60 is 3,600. So now I'm ready to go to my calculator and put this together then. Okay, so again, like to always try to do stuff in one step. So 15 times 0.349,065,8504. Okay, times 3,600. See, I'm just multiplying the numerator out. And then put that in parentheses, because you want the calculator to do that. And then the denominator, new set of parentheses now, you have 12 times 5,280. Okay, so I do that. Press enter. And we're going to end up with the answer 0.297. I'm just rounding the 3 decimals. I'm just choosing to do that. Miles per hour. Okay, so that's real slow. Okay, that's like less than a walking speed. Okay, so that's not very fast at all. But this wheel was only doing 3 revolutions in a minute, and if you can imagine that, I mean that's really slow. All right, so we expect this to have a slow linear velocity. You always want to try to make a connection between this. Okay, it's a real slow rotation. Therefore, it's going to be pretty slow. That's like a turtle's pace. Okay, that tire's not moving very fast. If it's only doing 20 degrees in a second, it's not moving very fast. Okay. Okay, all right. So let's try this out. Do the best you can. Really try to do it yourself. When I ask you on these recordings to do it yourself, I think it's real important that you take a little time to do that. You learn more from sometimes the struggle of doing something yourself than just watching somebody who's an expert do something. Okay? When I learned how to play guitar, as many years as I've been playing, it's been years and years of struggle, but I've watched lots of experts too who are better than I am. And the struggle and the watching, those two things, but mostly the struggle is why I can play. All right. So do your best on the next problem down below. Okay, and I haven't worked it out, but I did the way you should start this. So I'm just going to kind of talk about this, then we'll go through this together. So I drew a picture. Okay, I've got a bicycle. It has a wheel with a 20-inch diameter. Now, if you have a diameter, the radius is half of that, so it's 10. You need the radius because that's what's in your formula. The key to me to doing this problem is to understand that I gave you a linear velocity. Okay, so you want to use that letter V. V is 15 miles per hour. And you're wanting to find the angular velocity, so you're wanting to find omega. The formula that you got to use is V is R omega because you know V and you know R. We know these two things, two of the three things in this formula. Okay, so what I'm going to do is I'm going to solve this equation for omega. So I get omega is equal to V over R. All right, so now I'm ready to just start calculating. So omega is V over R. Okay, the linear velocity is 15 miles per hour. The radius is 10 inches. Now we got a whole bunch of unit conversions we have to do on this thing now, okay? So really one of the things that you want to do, and there's a ton of unit conversions in these problems, is you want to get to radians per minute, okay? So right now, let's just kind of focus on this piece kind of right here. We need to get miles and inches are got to cancel out. So we got to make miles and inches the same unit. So I'm going to convert probably miles to inches. It'll just be a real big number, but that doesn't make that much difference, okay? And you can do this in steps if you want to. So what I'm going to do, I think I'm going to rewrite this like this. I'm going to write this as 15 miles per hour and then over 12 inches, okay? So I'm going to go ahead and I'm going to do this. I'm just going to kind of work with this numerator right here. So I need to change miles to inches. So one thing that we know is we know that there are, in 1 mile, there's 5,280 feet. Okay, that gets rid of that. We also know that there are, in 1 foot, there are 12 inches. Now by doing that, see, those inches cross out now. Okay, and then also notice this, the feet cross out. All right, so we got that going away. So now we are in something per hour. And that's what we're after, is we're after radians per minute, basically. So we do need to change this hour to a minute. So I got one more conversion to do then. Okay, so I want to get rid of hours, and I want to end up with minutes in the bottom. So we know there's 60 minutes in 1 hour. Now, watch this real carefully now, because you've got to be real careful on something like this on your calculator. I think a lot of students sometimes do this problem better if they go through and do the conversions kind of step by step. So what I'm going to do is I'm going to focus just on this right here. Just on this. And if you look at this, all the units cancel off except the minutes. So I'm going to go ahead and do this on my calculator. You can't forget about the 12 that's in that denominator though then. So what I'm going to do is I got 15 times 5280 times 12. Now that will cancel that 12 out down there. You could also cancel that if you wanted to right there actually. And you want to get that. Okay, and then take that and divide that by 60. Like that. Okay, so I'm going to just write this down as another step. We have 15,840, and really now that's radians per minute. Let me write that a little neater there. So I have 15,840 radians per minute now. Okay, but then we have the divided by 12, so you can't forget about that. Now see, I could have canceled that out. Okay, if I wanted to, I'm just going to, you might not see that, so I'm going to take this, divide this by 12, and that'll give the answer. So that answer is 1,320 radians per minute. Okay, that's the answer you should have got. To me, you know, the hardest part of this problem is for most students is knowing what you're given and then knowing how to do all the unit conversions. Okay, the unit conversions is something that you got to get pretty skilled at. Okay, but there's alternative ways you could have done that. You could have immediately, if you wanted to, and some students might like doing it this way. If you start out with 15 miles per hour, well, if you're going to get radians per minute, well, then one thing that you might want to do is just go ahead and get this out of the way. So you know in 1 hour there are 60 minutes. Okay, so by doing that, you would have 15 divided by 60, if you calculate that, is 0.25, and then you would be miles per minute. Okay, so you'd have that. And then you've got the radius as in inches, so you would probably want to get that converted miles to inches or inches to miles. It doesn't make any difference. Just for something different, I'm going to do it this way. If I want to change this to miles, then I would do this. Okay, if you have 12 inches, there are 12 inches in 1 foot. Okay. Now hold on. You know what? I've been doing this problem and I don't know where the 12 came from. I think I really messed up and I have no idea why I did that. Okay, so I'm going to just kind of show you what I did here. And I do stuff like that sometimes. The radius is 10 inches. This right here should be 10 inches. Okay, so let me recalculate this. My apologies, I do that every now and then, and sometimes I just don't catch it when I need to. Okay, so I got to change that to 10, and let me recalculate this then on the calculator. Sorry about that. Okay, so let's do this then. Okay, so I just do the 15,840 divided by 10. So I'd end up getting 15,084 radians per minute. Okay, so that's the idea. All right. So that'd be one way to do that. I am going to just kind of do what I was doing over here. So again, if you had the linear velocity is 15 miles per hour, and if you multiplied that to change that to miles per minute, you would have in 1 hour there's 60 minutes. Okay, so that would give 0.25 miles per minute, like that. And then you got the radius, so the radius is 10 inches. That's how I caught my mistake. Okay, just for something different, let's change this to miles. So there's 12 inches in 1 foot, and there are 5,280 feet in 1 mile. Okay, so right now, if I do this conversion, well, then this is going to be in miles now. Okay, so if I do this, you're going to have a decimal part of this, then we would just do 10 divided by parentheses 12 times 5280. And then that would give you this, okay, which is a real small number, 1.5782828. It looks like that's just repeating 2 8s probably. That's good enough. I'll just round it off there. Times 10 to the negative 4 power in miles. That's a real small number of miles. Okay, so then what you could do is the formula that we have again is omega is V over R. So if V is this, 0.25 miles per minute, sometimes I have a hard time writing on this, miles per minute, and then divide by the radius, which is 1.5, let's just round it like that. Okay, then what happens is this crosses out, so you're going to be in radians per minute like we needed to. And then you would put this on the calculator like this. You go 0.25 divided by, and you don't need parentheses because it's one number, 1.58. And then E, negative 4, should get about the same answer. Okay. So look at that. See, we're about the same. And I'm off a little bit because I rounded. So you might find this approach a little bit easier. I don't know. I can see that a student might understand this a little bit better than what I did over there. I was trying to do all the units in one calculation. Okay, and let's see. The last thing here is how many revolutions does it make in a minute? Well, this is just a simple conversion. So we have radians per minute, and we want to change that to revolutions per minute. Okay, so I'm going to do this. First thing I'm going to do is change radians to revolutions. So radians converts to revolutions. What's the connection? 1 revolution is what? 2 pi radians. Good. Okay, now we want to do that. That's all we got to do, just get our calculator. So now we're in revolutions per minute. Okay, so I just do 1584 divided by parentheses 2 pi. Be sure you do the parentheses again. And there we have it. Oh, in the world did I just do? If this ever happens, you get a syntax error, go to go-to, and it usually will tell you where that error is. See, I didn't type that in right at all. Gosh. Okay, what in the world did I do? Okay, so I just need to do the 2 pi. Oh, that's all messed up. I'm just going to start again. So 1584 divided by parentheses 2 pi. Okay, so that will end up giving me about 250 revolutions per minute. Okay, so what it's going to be, every time that 1 minute goes by, you go through about 252.1 revolutions. So that's the idea. Okay, so that's it. All right, so you kind of get into an idea what you're getting into here. I'm going to do one more example to finish this up. And this is one that is kind of a typical physics problem. It's got a lot of stuff going on in the problem, a lot of concepts. So to finish up on this last page, last but not least, we're going to look at this problem. And what this problem says is you have 2 sprockets. The chains are 9 inches and 3 inches. The larger sprocket rotates at 36 times per minute. You're going to find the angular velocity of the smaller. And that should have been smaller sprocket instead of pulley. Okay. So what I'm going to do is I'm going to draw a diagram. I'll have you draw a diagram. So let's just kind of draw what we know that a bicycle tire look like. So we have that. And then let's draw the smaller sprocket. We're doing sprockets actually, not tires. So it's kind of like your chain going like that. And then around that, you got your chain connecting kind of like this. And then they're rotating. All right. Now, what we're given in this problem is it looks like we're given that. Nah, not that. I want a line. So I've got a line representing my diameters. Okay, and what we're going to say on this, I'm going to say the diameter of the big is equal to 9 inches. Then I'm going to say the diameter of the small equals 3 inches. Okay, so the big sprocket is 3 times as big as the other one. All right, now I'm going to kind of write down what we're given on that. So we're given the diameters. Well, we need to change these to radius. So that means the radius of the big would be half of 9, which is 4.5 inches. And then the radius of the small sprocket would be half of 3, so that is 1.5 inches. Okay, now here's the next thing. The larger sprocket rotates at 36 times per minute. So the whole key is, what did I give you? I'm giving you a rate. It's either got to be linear or angular velocity. Which is it? Okay, that's angular velocity because it's rotations per unit of time. Exactly. So what we're going to have also is the angular velocity of the big is 36, and that's really saying revolutions per minute. Okay, that's what we have. All right. Now, this is what we're given. This is all you're given in this problem is this information. What you're going to try to find is the angular velocity of the smaller. So you're going to find the angular velocity of the smaller pulley like that. Well, you have to go through kind of a series of calculations to do this now. So the first thing that we got to do is, if we're working with these formulas, we have to change this to radians per unit of time. So what I'm going to do over here is I've got the angular velocity of the big is 36 revolutions per minute. So I'm going to change that to radians per minute. Like we've been doing, 1 revolution is 2 pi radians. We want to have this in radians per minute. Okay, so that means the angular velocity of the big pulley, and we'll just use decimals on this, I think, or actually I'm going to leave this as whole numbers, I think. Yeah, I think it's better if I do that. So 36 times 2 is 72, so that will be 72 pi, and we end up with radians per minute. Okay, now there's an important connection on this, and I'm going to go back to this thing that I showed you a little bit earlier on this demonstration. I'm going to go back to this website and show you this again. Now what we have here is you have an angular velocity, you have a big and a small sprocket. But what I want you to understand is this, I showed this a while ago, is the rotational or angular velocities are different. Okay, the smaller sprocket is rotating faster than this one. However, this red dot, which represents the linear velocity, is always the same. So on a bicycle chain on the sprocket, that chain is always moving at the same rate, because if it wasn't, it'd get all tangled up and stuff, right? So I want you to think about and understand that the linear velocities are equal, see? No matter what the size of these sprockets are, those angular velocities don't change, okay? So the key thing on here, to me, is the whole key is the linear velocity of the big sprocket is the same as the linear velocity of the small. That's a real key thing to understand on this problem. So what I'm going to do as a result, I'm going to go ahead and kind of go like this. So now I have the angular velocity of the big is 72 pi radians per minute. What I'm going to do is I need to find the linear velocity of the big. And then if I find the linear velocity of the big, that will be the same as the linear velocity of the small, and then that's all I need to figure out the final answer of the problem. So we have the formula V is equal to R omega. Okay, so that means all we got to do on this is take the radius, and we're doing right now the velocity of the big. So we're going to take the radius of the big, which is 4.5 inches. And we're going to multiply that by the angular velocity, 72 pi radians per minute. Okay, so I'm going to take my calculator and do that. So if I do 4.5 times 72, I'm just going to leave pi. I'm not going to use the decimals for pi. That's going to give me 324 pi. And then radians is not a unit, so it's actually inches per minute. Okay, so we got that. Now, since the linear velocity of the big is equal to linear velocity of the small, therefore, the linear velocity of the small is 324 pi inches per minute. Okay, that's the whole key to the problem, is get down to that point. Okay, so finally, here's what we're trying to find. Okay, we know that the linear velocity of the small is equal to the radius of the small times the angular velocity of the small. Now what we're trying to do is we're trying to find this. Okay, now we know everything. See, we know the linear velocity of the small. We know that's 324 pi. We know the radius of the small is 1.5, see. So we're ready to rock. Okay, so I just divide by the radius, and then we're ready to get the final calculation going here then. Okay, so the linear velocity, or the angular velocity of the small is the linear velocity of the small over the radius of the small. Okay, so we know this. We know the linear velocity of the small is this. So that's 324 pi inches per minute. We know the radius of the small is this guy. So we have this. Okay, now what's going to happen is those inches are going to cross out, and we're going to end up with radians per minute. So I just take my calculator and do 324 divided by 1.5, and that gives 216. Okay, so the angular velocity of the small is going to be 216 pi radians per minute. Okay, now I'm going to do one more thing of this problem. I'm going to go ahead and change this to revolutions per minute because I think you'll understand a connection in this problem a little bit better. Okay, I'm going to highlight two things here. I'm going to highlight this, and I'm going to highlight this to begin with. Then I'm going to do one other thing. Okay, so I'm going to do this. We're going to take the 216 pi radians per minute, and I'm going to change that to RPMs. So I've got there's 2 pi radians in 1 revolution. Okay, so I'm going to do this calculation. See, the pi's are going to cross out. And then if I do 216 divided by 2 is 108 revolutions per minute. Now, I want to show you something on this. Okay, so the answer to the problem can either be written as this or this. That's your final answer. Okay, so this would be your answer. This would be your answer. 2 ways to write that. But I want to see if you can make a connection on something here. Okay, and this is pretty important. You may have already made this connection. You may have made it at the beginning of the problem. It depends on what you see here. So here's what we had. We found that the angular velocity of the big is 72 pi radians per minute, and we found the angular velocity of the small is 216 pi radians per minute. We also began with the angular velocity of the big was 36 RPM, and we just now found that that is the same as 108 RPM. Now my question to you is, what is that connection? Does anybody know? Okay, let me ask you this. In the beginning of the problem, what was the connection between the diameters? Yeah, one of them was 3 times bigger than the other. Well, let's see if what happens here. Look what happens. If I do 36 times 3, my God, I get 108. That is the connection on that. It's very fascinating to me. All right, so the thing is since the diameter of the big was 3 times the diameter of the small, then it turned out to be this then. All right, so basically it turned out that the, and I'm going to do this like this, I'm going to write this like this. The angular velocity of the small, which is 108, how does that relate to the angular velocity of the big? Okay, well, one of these is 3 times bigger. Okay, so that angular velocity of the small is also 3 times faster. So it's got to rotate 3 times faster to keep up with that speed, okay, to keep up with that distance that bigger one is traveling. So hopefully that makes some kind of sense to you. All right, so you're probably saying, man, you mean I could have answered this question without going through all this crap? Well, yeah, kind of, but you know, if you don't, but I mean, I'd hate to just tell you that without doing math, but you know, this is the math that verifies that. Okay, that'll wrap this up. This is a really challenging section for a lot of students, so let me know if you need help or anything on this. And when you're reviewing the notes on this, you know, go through it more than once if you have to. And the key to solving these problems to me is always writing down what you're given, write down what you're finding, and then pick the right formula to use. Okay? All right, good luck. Let me know how you do.